Hi guys, myself Pranav is here to deliver today's presentation, Power Transformer Part 55. As the subject is of the continuation, so for your convenience, the link of the previous one is given under the description box. Let's start with distinctive constructional features with typical magnetic circuits and winding configuration. As of the typicality in placement of core and winding configuration, it has already been discussed that power transformers are of two types, that is one, core type and shell type. For core type transformers, the windings are being encircled on the core, while in shell type transformers, the core that has to encircle the windings. This is the basic difference in between core type and shell type. Their performance must have to be depend on the basic designing configuration of magnetic circuits in combination with typical selection and arrangement of winding connections. Analyzing the key constructional features, it has been exhibited that the shell type construction is being more complex as compared to a core type. See the core type transformer configuration, concentric winding or cylindrical winding placed on the limbs. Shell type transformer windings, which are interleaved or sandwiched on the central limb. For the same MVA rating, more electromagnetic material is required to construct the core of shell type transformer as compared to core type configuration. But so far, winding protection is concerned, it is more safer in shell type than in core type. For shell type transformer, there would have been much better in leakage magnetic flux control than that of the core type configuration. Shell type transformers are basically more resilient to short circuits in the transmission systems and are mostly preferred to use in variable industrial applications. That is, special type of industrial applications. Shell type transformers are often used in railway traction system where a limited amount of space is available. In a shell type transformer, the average length of magnetic core is comparatively shorter. Hence, the shell type transformer that has to provide a shorter magnetic path. Thus, it requires smaller magnetizing current. Whereas, the average length of winding is comparatively longer and that results in higher percentage impedance. As of the constructional features, a shell type transformer has always to provide better support against the electromagnetic forces between the current carrying conductors. Single or three-phase shell type transformers of unit ratings up to 1300 MVA with having primary voltages up to 765 kV are being available at the present market. However, for the higher rating shell type transformers, there must have a forced air and or forced oil cooling system is evidently essential, as because heat generated during operational situation cannot be get dissipated easily from windings due to surroundings of it is surrounded by yoke and limbs. Manufacturing cost as well as repairing or dismantling cost of high voltage and high MVA rating shell type transformer would have been significantly higher as compared to court type transformer. The court type transformer, as because it offers relatively easy assembly of windings and insulation with having simple type of electromagnetic court structural configuration. So, the end users of electrical transformers often prefer to use court type structures rather than shell type structures. Difference between court type and shell type transformers. Configuration wise, that is magnetic circuit for court type consists of two vertical sections called limbs and two horizontal sections called yokes. Whereas for shell type consists of one central limb and two outer limbs. Number two, windings to be placed in case of court type placed on two separate limbs where LV winding is placed next to the core and the HV winding around the LV winding. For cell type, both primary and secondary winding are placed on the central limb. As of the type, in case of court type, the windings surround the magnetic core, whereas in shell type, the magnetic core surrounds the windings. Shape of core laminations. In case of court type, U and I-shaped laminations are used to construct the core. Whereas shell type, either U and T-shaped or E and I-shaped laminations are required. Cross-section of core. It may be square or cruciform, two-stepped and three-step type for court type. Whereas in shell type, shape is rectangular. Number of limbs and yokes. For court type, 2 limbs, 2 yokes. Whereas shell type, 3 limbs, 2 yokes. Number of magnetic circuits, a single magnetic circuit in case of court type, whereas for cell type, 2 magnetic circuits. Type of winding, concentric winding for cylindrical winding, concentric winding or cylindrical winding, whereas for cell type, sandwich winding or interleaved winding or disc winding. Conductor material. More conductor material is required for windings in case of court type, whereas comparatively less quantity of material required for windings in case of shell type. Material for core formation, requires less ferromagnetic material for core formation in case of core type, whereas in shell type, comparatively more quantity required for core formation. Core loss. Core loss is more as because total magnetic flux flows through the entire core. But in case of shell type, core loss is comparatively less as because half of the total flux flows in the entire core. Copper loss is more in case of core type. Copper loss is comparatively less. Natural cooling process in case of core type relatively more effective due to distributed windings, whereas shell type it is not so much effective as because the magnetic core surrounds the windings. Repair and maintenance. For core type, it can be easily executed, whereas in shell type, relatively much more difficult to execute. Average winding length comparatively shorter, and that leads to lower percentage impedance in case of core type, whereas in shell type, relatively longer, and that leads to higher percentage impedance. Average core length. Average magnetic core length is comparatively longer in case of core type, whereas average magnetic core length is comparatively shorter in case of shell type. Tank heating criteria for three-phase transformers, as there is no path to flow, zero sequence flux, so it has to flow through the air gap, and that causes heating of the tank in case of core type. But for shell type, as the transformer provides path to flow zero sequence current through its lateral legs, so there would have been no cause of tank heating problem. Efficiency. Comparatively higher with the core loss as well as copper loss, which indicates relatively lower efficiency in case of core type, whereas for shell type comparatively lower with the core loss and copper loss, which indicates relatively higher efficiency. Preference in application. For high voltage and high power application, core type is preferred. But shell type is suitable for low voltage and low power application. Classification of transformer according to their application. There are several types of applications, that is exclusively for power transformer. Another is distribution transformer. Power transformer mainly used in generating stations or in the main substations. Distribution transformers for distribution purpose. Instrument transformers. Testing transformers. Special purpose transformers. Isolation transformer. Impedance matching transformer. And last one, autotransformers. Power transformer is mainly installed at the generating station to step up the voltage for transmission purpose and voltage to step down at the receiving station. Large capacity and designed with low copper losses for obtaining high efficiency, meant for operating at high average load continuously. Distribution transformers for distribution stations to step down voltages meant for operating 24 hours with having load fluctuation from no load to full load, designed with low iron losses for obtaining high efficiency. Instrument transformers to measure the system high voltage and current by potential transformers, that is PT, and current transformers, that is CT. Incorporate with protective devices also. Testing transformers, voltages are being stepped up to a very high values for carrying out tests, as for example to measure the dielectric strength of transformer oil or any high voltage tests. Special purpose transformers to act as special purpose, as for example associated with furnaces, rectifiers, welding sets, etc. Isolation transformer only used for electrical isolation between two AC circuit without any transformation of voltage or current levels. That is, transformation ratio may usually be 1. Impedance matching transformers used at the output stage of the amplifier for impedance matching to obtain maximum output from the amplifiers. Last one, autotransformers. Autotransformer. Autotransformer is the single winding transformer in which a part of the winding is common to both the primary and secondary circuits. Hence, in an autotransformer, the primary and secondary circuits are not at all electrically isolated. Rather, a section of the same winding acts as secondary or primary of the transformer. As the single coil series, as the single coil serves as a part of both the primary and secondary windings, so different voltages are thus to be obtained by providing multiple tapping or connecting at different points along the winding. There are at least 3 taps that would have been taken out for the electrical connections, out of which 2 taps are meant for connecting the voltage source and the electrical load. The remaining tap at the end of the winding that has to serve as a common connection to both circuits. Autotransformers are frequently used in power transmission and distribution network for having the application to interconnect systems operating at different voltage classes. Autotransformer has the basic characteristics to provide a more constant output voltage under varying load conditions than does the two winding type transformer. However, the physical arrangement of an autotransformer is shown in figure. As of the figure, the primary and secondary currents are 180-degree out of phase and tend to cancel it in the portion of the winding that is common to both primary and secondary. Such phenomenon is an important technical aspect of using autotransformer instead of two-winding transformer, where the principal application is there to be of voltage ratio not less than about 2 is to 1 and is not being essential to have the electrical isolation of the primary from the secondary circuit. In case of two winding transformer, where there is no physical conductive connection between primary winding and secondary winding, and the transfer of power from primary winding to secondary winding is thus to be carried out through a time varying magnetic field linking only by the process of induction phenomena, that is self induction and mutual induction process. For conventional type two winding transformers. But as of the typical configuration of auto transformer, where there is a physical conductive connection between primary winding and secondary winding. That is, the windings are thus to be coupled both magnetically as well as electrically. Because of its entire winding is being placed on a single magnetic core, so transfer of power from primary winding to secondary winding would thereby to be carried out by means of both in electrically through conduction process as well as in magnetically through induction process. Single phase autotransformer are often used for providing required conversions between the two common domestic mains voltage bands. For higher voltage classes, it is normally to prefer three-phase autotransformers with taps at the common neutral end. Autotransformers, as of the performance, are of three types of construction. One, single-phase autotransformers, three-phase autotransformers, and variable autotransformers, as for example, variac of having a sliding tap. Single phase autotransformer, that is step down configuration. In general, the part of the winding which is common to both the primary and secondary winding is called the common winding. And the rest of the autotransformer winding is called the series winding. See another diagram, that is step up configuration. As winding is common in both circuits, most of the energy is transferred by means of electrical conduction and a small part is transferred through magnetic induction. Autotransformer has the basic characteristics to provide a more constant output voltage under varying load conditions than does the two-winding type transformer. It is important to note that all the power is not traveling through the winding of the autotransformer primary to secondary. This has happened as because the primary and secondary currents are 180-degree out of phase and rather tend to cancel in the portion of the winding that is common to both primary and secondary. Electromotive force as induced in the winding is proportional to the number of turns. So the secondary voltage that can be varied by just varying a secondary number of turns. operating concept of step down and step up autotransformer. As of the figure 174, once AC voltage Vp is applied to winding AB, then an exciting current starts flowing through the winding AB. As the intent or leakage impedance, as the internal or the leakage impedance drop is being neglected, then voltage per turn in winding AB Vp divided by N1. That is equation number 1. Therefore, voltage across BC Vp by N1 into N2. Current I2 would thus to flow through the load when switch S is closed, and current I1 is thereby drawn from the source. As the losses are not being considered, so input equals to output power. That is Vp I1 cos phi 1 equals to Vs I2 cos phi 2. As the internal or leakage impedance drops and losses are not being considered, so in this case, the power factor of both the primary as well as the secondary would be the same. That is cos phi 1 equals to cos phi 2. Hence, from equation 3 and 4, Vp I1 equals to Vs I2. For an output of I2 at voltage Vs, then the input will be I1 equals to I2 into N2 by N1, while the applied voltage is Vp equals to Vs into N2, N1 by N2, or Vs by Vp equals to I1 by I2 equals to N2 by N1, that is equal to K. For the figure 174, that is figure 1, the value of K will be less than unity. The magnetic induction process in all types of transformers would have to work under the fundamental laws of electromagnetism, that is Lenz's law and Faraday's first law of electromagnetic induction. Again, I repeat, the magnetic induction process in all types of transformer would have to work under the fundamental laws of electromagnetism, that is Lenz's law and Faraday's first law of electromagnetic induction. According to Lenz's law, where it is clearly formulated that the direction of current as induced in a conductor by a changing magnetic field is such that the magnetic field created by the induced current would have to oppose changes in the inertial magnetic field. Faraday's first law of electromagnetic induction, where it is stated that whenever a conductor is placed in a varying magnetic field, an electromotive force is induced. If the conductor circuit that would have been a closed one, then as of an effect of this electromotive force, a current is thus to be induced on that conductor circuit. Therefore, When an alternating current is applied to the primary winding of the autotransformer, then an electromotive force is induced in its primary part. As the conductor is in stationary condition, but the magnetic field is alternating in nature. So, a flux is produced in the primary part by the induced electromotive force, and that is called primary winding magnetic flux. Again, I repeat, as the conductor is in stationary condition, but the magnetic field is alternating in nature. So, a flux is produced in the primary part by the induced electromotive force, and that is called primary winding magnetic flux. This primary winding magnetic flux, as soon as it is associated with the secondary winding of the autotransformer, an electromotive force is thereby to be induced in the secondary winding through mutual induction. The magnitude of induced EMF is determined on the basis of the number of turns of the secondary winding. The generalized equation is primary winding electromotive force E1 and secondary winding electromotive force E2 equals to N1 by N2, where number of turns of the primary is N1 and number of turns of the secondary is N2. In conventional two-winding transformers, the core is the primary source of flux linkage between primary and secondary winding without any electrical link, and that is why it is called a magnetically coupled machine. That is, two-winding transformers are magnetically coupled machine. But as of the working principle, an autotransformer having with single winding is thus to be designated in both electrically and magnetically coupled device. This is the main difference in between the conventional transformer and autotransformer. From figure 174, it is to understand, sorry. From figure 174, it is to understand that the exciting current once starts to flow in direction A to B, then the working magnetomotive force would have to act vertically upward in the core, that is, in direction of B to A. At any instance, while the breaker switch S is closed, then the current I2 would have to flow from B to C, and the corresponding magnetomotive force would have to act vertically downward in the core. As of the consequence, that magnetomotive force would thereby have to oppose the exciting or working magnetomotive force. At no load condition, the exciting current I1 as flows through the winding AB and for which the exciting or working magnetomotive force as generated, that would have to remain constant. But under the load condition, the connected load would have been drawn current I2, and that current is flowing from B to C. The current I1 is to flow from C to B, so the current IBC equals to I2 minus I1. Here I2 is greater than I1 as Vs is rather less than Vp. Now, the magnetomotive force as produced for winding part AC equals to I1 into N1 minus N2, and from equation 9, magnetomotive force as produced for winding part CB equals to I2 minus I1 into N2. Power transformed in winding part AC, that is VAC into IAC equals to VP minus VS into I1, and is expressed in volt ampere. Total input power expressed in volt ampere is VP I1 from equation 13, 14 and 8. Power transformed in winding part AC divided by total input power equals to Vp minus Vs I1 divided by Vp I1 equals to 1 minus Vs by Vp equals to 1 minus K. Therefore, power transformed equals to 1 minus K into total input power. From the expression, it is thus to be concluded that 1. The transformer action would have taken place between winding section AC and winding section BC. Due to transformer action, out of total input power of Vp I1, B power only to be transformed equals to Vp minus Vs into I1. Remaining power that has to act directly to the secondary from the primary, that is power required for the output. Due to transfer action, out of total input power of Vp I1, power only to be transformed Vp minus Vs I1. Remaining power that has to act directly to the secondary from the primary, that is the power required for the output. Output power equals to power input minus transformed power, Vp minus I1 minus Vp minus Vs I1, that is Vs I1. Now output power by power input Vs I1 divided by Vp I1 equals to K. Therefore, output power equals to K into power input. With these working principles, autotransformers are essential for multivarious applications and are designed to provide the voltage regulation in electrical grids or voltage transformations in industrial machinery or phase shifting capabilities. Let's stop here, further to be continued at later stage. Thank you. Thank you for listening the video. Kindly do like, share and subscribe. Your subscriptions would encourage to post more videos. Also share your comments or feedbacks inside the dedicated comment section. If you have any suggestions or specific topic you want, then let me know in the comment section, please. Thank you. Thank you for patient hearing.